we have done fitting the model and predicting the model, applying the model on the unseen data to make a prediction. Now our next objective is we need to check, we need to understand how the model output, the output produced by the model. Look here, this is the one, the model output, dot summary. It gives me the linear regression model output. And what is the dependent variable that we have used it? So price, in this case, the model is OLS. Now the question is, you might be asking this, and why we need to use sklearn to train the model, and why do we need to use stats models once again to train a model? Okay, so here the reason is with OLS function, you can get the detailed output like this. Whereas in the sklearn, the limitation with this one is it cannot produce a model output with a model with detailed output like this. Okay, so that is the reason why we are using the OLS method that is available as part of the stats models. And here we can see that the price, because end of the day, interpreting the model output is very much important, and you need to convey the outcome of your model to your executives or senior management. Okay, so dependent variable is the price and model is OLS, ordinary least squares method. What is ordinary least squares method? So using the objective of the ordinary least square method is to minimize or estimate the value for your coefficients, the beta naught, beta 1, beta 2. Right, so estimate the optimal values for your beta naught, beta 1, beta 2 in order to minimize the errors. Okay, and then the method is a least squares method, and which date, which time, and number of observations on degrees of freedom, residuals 145, model is 2, and here R squared is 0.895. So what is R squared? The R squared value should always be between 0 and 1, 0% and 100%. So if it is 0%, if it shows 0, that means the model explains none of the variability of the response data around its mean. Okay, if it is 100%, it indicates that the model explains all the variability of the response data around its mean. That is what it represents. The proportion of, in simple term, the proportion of variation explained by your independent variable on the dependent variable, right? So 0.895. With the independent variable here, the size and UDS, whatever I used it, my model was able to, with these two variables, my model was able to explain the outcome variable price with 0.9. So any value which is closer to 1 is the good. So in this case, it is somewhat close to 1, hence my model is doing good. Okay, we can conclude that way at this moment. In simple term, R squared is the percentage of variability explained by the model. So what is the unexplained variation? The remaining thing. So 1 minus 0.895. Let's say no, this is 0.90. So remaining 0.10 was not explained by my model with these two variables. That means error. We have 0.1 or 10% of error. We have it 0.90%. Sorry, 90% of the variation was explained by these two variables. Remaining 10% was not explained by my model, which means that is an error. And we have something else called adjusted R squared. So adjusted R squared, gives the correct value in the case of multiple linear regression. Always, most of the cases, the adjusted R squared values less than your R squared value. Look here, the adjusted is 0.894, whereas it is 0.895. The R squared is, it is a bit biased one. When you keep add variables, for example, size plus UDS, plus if you put a park plus MASC variable, what will happen? R squared will get inflated blindly. Though price and, the park and MIS, those two variables were not statistically significant, which means those two variables are not helpful. So these two variables are highly correlated, and also these two variables are not at all correlated with the target variable. Then there is no point in including that. But when you include these two variables also as part of this model, For example, size plus UDS plus par plus MASC, if you put it, R squared will blindly, get inflated. It will increase. It'll be biased. Okay, because those two variables are not at all statistically significant, which means those two variables are not correlating with my target variable price. Even though it is not, correlating with my target variable, blindly my R squared value increases. It is not giving me the clear picture. Okay, whereas adjusted R squared, it penalizes the variables that are not significant. Even if you include park and MISC, the adjusted R squared, what it does is it simply penalizes those variables are not contributing, or those variables are not helpful in explaining the outcome variable. So I'll just give you a simple analogy. Guys, please concentrate. For example, in a project, 5 members are there. Okay, and your senior management, you are in a status call, you are a project manager. During the status call, your vice president is asking you the call. So he is asking the question. According to him, if he gives more number of people headcount to your project, right? So your project, you should be able to complete the project on time or well ahead of the schedule. That is what their expectation. That is what their perception. Okay, the vice president is asking you, hey, I gave you 10 people. Blindly, when you give 10 people, what will happen? When you add more number of variables, your R squared will be more. It is biased, but this is what their view. Whose view? The vice president view. They think, I gave you more number of people, it should be the productivity should be more. But as a project manager, you know very well, all out of the 10 guys, 5 guys are not doing any job. Blindly, we have recruited, onboarded 10 people, but of the 10 people given by my vice president, right, only 5 people are actually working. Remaining 5 people are dumb guys. Okay, they are completely useless in terms of, because they are not trained on machine learning model, or simply they give some people just by having increasing the headcount. Do you think the productivity will increase? No, right? So your manager is something like adjusted R squared. He is going to penalize. No, out of 10, only 5 people are contributing. This is what the actual productivity for the current team. Something like this is a simple analogy. Okay. So adjusted R squared, I'll explain you with formula why, what is the exact difference between R squared and adjusted a little later. At this moment, you just keep this in your mind. Okay. This analogy. Okay. Adjusted R squared will always penalize the features that are not explaining the outcome variable. That is the beauty of adjusted R squared. So in the case of multiple linear regression, you will have to rely on adjusted R squared. In the case of simple linear regression, you can go for R squared. Yes, recording going on, Gilbert, yes. And we have something called F statistic. So during the ANOVA test, we have discussed, right? So F statistic and probability of statistic is this one, and the log likelihood. See, this F statistics will tell you, or the p-value, this p-value is related with your F statistic. If the p-value is less than alpha, that means in the overall, how the model is performing with respect to the features, whatever we have used it here. This gives you an eye-level idea about your features, okay, the independent variables. So this one, E minus 72, that means 0.00072 zeros, 71 zeros, you need to prefix, right? The p-value is very, very small here compared to your alpha. Alpha is 0.05. Hence, we are going to reject the null hypothesis, saying that the features, whatever the alternative is, whatever the variables, the independent variable which we are using it here is contributing in terms of explaining the variability in my outcome variable. This gives you an overall idea. Okay, it will not give you feature-wise the whether it is statistically significant or not. That it will not give you overall model. Okay, at a high level, it gives you it's something like that. It's something like that, right? So when somebody is saying you are overall, when they see you outside, you are doing good, but still you have some injury in your leg, mild injury. All right, still you have injury, but still overall you are doing good. Overall you are doing good. That doesn't mean you are completely 100% fit, right? something like this. The p-value associated with the statistic is very, very less. Hence, we are going to reject the null hypothesis, and we are going to conclude that the independent variables, whatever we use it in this model to train it, are statistically significant, which means these two variables are contributing in terms of predicting the outcome variable price. We have log likelihood. Log likelihood, I will discuss it later as part of the logistic regression. At this moment, let us not worry about this. So next one is AIC and BIC. AIC stands for Archaic Information Criteria. I just show you here. See, I put it everything here in detail here. So the AIC stands for Archaic Information Criterion. It is a matrix used to compare the fit of different regression models. Like I said, so in this model, we have used two independent variables. And you create another model wherein you include 4 independent variables. And check what is the AIC for that model. So you created one model for that. For this model, this is the AIC value. Okay, this is the AIC value. And if you create another model by including 4 independent variables, you need to check that AIC value. Of these two models, whichever model has lesser AIC, that is the best model. This is another way of doing the model selection. And apart from this, we have something called Bayesian information criterion. Okay, this metric is used to compare the goodness of fit of different regression models, same as the AIC. Okay, we fit, let's say you fit several regression models for the same data set, and ultimately you are going to choose the model with the lowest Bayesian information criteria value as the best fit for your model. So AIC and BIC more or less same. Okay, and the goodness of it, right? So here also the same thing. So create another model with the size plus UDS plus MISC plus PAR, and what is the BIC value? That BIC and this BIC. Let's say that BIC is 594, here it is 592. So compared to that model, this model is better. Lesser the AIC, lesser the BIC, tells you that is the best model. Okay, best fit model. And then apart from this, if you see here, this is a very important thing. Your management, they are not going to be aware of what is R squared, adjusted R squared. As a data scientist, you should be knowing, or you will be knowing what is, you should be knowing what is R squared, adjusted R squared, how to interpret them, what is AIC and BIC. AIC and BIC are helpful in terms of, finding the goodness of fit of the model. Okay, and the adjusted R squared in the case of multiple linear regression helps you how much percentage of variability explain your model. Okay, this is very, very important. This topic, okay, this place, okay, it gives you the coefficient value for each coefficient. You know what is slope and what is intercept. Since in this case we have two independent variable, two slopes are there. Okay, instead of saying beta 1, beta 2, see intercept is very well, right? The intercept is the line where it touches the y-axis called your intercept. Or in other words, if the value of independent values or variables are 0, and what is your estimated housing price in this case, right? That is what your intercept, and intercept is 3.00. So this is beta naught, and size is beta 1 and beta 2. Instead of displaying beta 1 and beta 2, it mentioned the slope value. The slope value it mentioned with the name of the independent variable itself, so that when you look at this one, okay, this is beta 1, which is nothing but the size. It gives you should understand, right? If you have 100 independent variables, if it displays something like beta 1, beta 1, beta 2, beta 3. So what is beta 3? What is beta 4? If it displays with some meaningful name, you should be able, oh, this coefficient value is related to size. This is the slope value for the variable size, and this is the slope value for the variable UDS. Got it? Okay, so that is what it tells us. So now the question is, how do we interpret the intercept? See, the CEO or company vice president level or senior guys, they are when you present the model output to them during a status call. So they don't care about all these things. But in that call, not only vice president, the business people are there, along with them, the data scientists are also there from the American side, okay, or the customer side. But those data scientists, they know all these things. They will ask you what is asked, what is adjusted, ask why the adjusted is only this one, what other efforts that you have taken in order to increase this one. Did you include all the necessary features? Why only these two variables? Something that they'll ask all technical questions. And these people are business people. Okay, for them, you need to explain this from the business language, in the business language. What is intercept? If the size of the house is 0, if the size of the house is 0, or the UDS is 0, so we would expect the housing price is 3.0074. The average price of the house, see the average of the housing prices, the expected average housing price is 3.0074 when the size is 0 and the UDS is 0. That's how you need to explain. And what is size? Size and UDS are coefficient, the beta naught and beta 1. And here, if the size of the house increases by 1 square feet, so we would expect the housing price to increase by 0.04, holding other variables constant. So holding other variables constant. This is very much important because this is a multiple linear regression. In the case of the simple linear regression, we don't have to use this term holding all the other independent variables constant. I'll just go back here. See, so this coefficient, right, tells you how much the dependent variable is expected to increase when that independent variable increases by 1 unit, holding all the other variables constant. This is very much important. Okay. And similarly, UDS, right? If the undivided share of the housing price, so if the undivided share increases by 1 square feet, we can expect the housing price to increase by $0.1797 or something else, okay? Holding other variables constant. This is how we need to explain them. And if you look at the end of this one, right, intercept, size, and UDS, you will find 0.975, 0.025 is kind of a, the interval. All right. So here we can say that with the 95% confidence, we can estimate that. Let's take, for example, in the case of size, right? With 95% confidence, we estimate that 1 square feet increase in size results in 0.44 to 0.50 increase in price in US dollars. So they are giving you remember the confidence interval I discussed, right? So now the question is, see, we have taken a sample, customer has given the data set, and we have sampled it with 70% of the data as randomly we sampled the given data as the training data set and test data set. So whatever the data we received was itself a sample data, right? So what is the assurance when I use different sample, the 1 unit, right? What is the expected increase in housing price when 1 unit increase in size, right? So does this still holds good for any type of sample? That is where we can see, even if you repeat the, if you train the model on different train and test set, you can expect between these two ranges, right? So there is a 1 unit increase in my square feet. So we can expect the housing price to increase by 0.400, so we can expect the housing price anywhere between 0.044 to 0.050 increase in price in US dollars. Since this is a positive value, right? So there is a positive correlation. There is an increase. If it is a negative value, so there is a decrease in value. You need to say decrease, okay? This is how you need to interpret the model outcome. Okay, now the question is, what is standard error? Standard error is an estimate, or the standard error, this is the one measures the accuracy of the size, like 0.002 measures the accuracy of your size if the same test were run on a different sample of your population. There will be some variation from sample to sample, right? When you fit a model, the coefficient value will change. What is the assurance? The slope for size is always 0.04. What is the assurance that UDS will, the slope value for the UDS will 0.17 if I run the test with different sample of our population? That is where the standard error is coming into picture. The standard error, we use it, or the standard error here, right? So computed. So with this, we can, so this is used to compute an estimate of the expected difference in case you run the model again and again, right? So what is the expected difference? So now the question is, if I run the model with different train and test schedule, will it remains the same? No. So there is a, in the range, 95% confidence, the price can range. And with the standard error itself, right? With that only we can tell this one, right? So with this one, so the we are right. So this is the estimate of the expected difference. Expected difference if we run the model and again with the different train or test set. Okay, that is what the standard error is all about. The next one is the T statistic. The T statistic is the coefficient value divided by standard error. You will get this one. If you divide this one by this one, you will get this value. And if you divide this value by this value, you will get the T statistic. Okay. This is what T statistic. And finally, you have P values. The P values for the coefficients. For example, size, the P value is 0, and UDS, it is 0. Even for the intercept, it is 0. So the P values for the coefficients tells us whether these relationships are statistically significant. Yes, size and housing price is statistically significant. And UDS and housing price is statistically significant, which means these two variables are helpful in terms of explaining the variability in my target outcome variable price. So in simple plain English, these two variables, including these two variables in this model really makes sense. And if I include the park and MIC, it is not at all making any sense. So that with the help of the correlation matrix itself, we can make out, right? So those two variables were not at all correlating with the target variable housing price. Got it? So this is very much important. The model coefficients, and I explained you what is standard error, what is T statistic, and probability of T everything. See, here also I mentioned everything. Don't worry. Okay. So this material will get into my website maybe this Monday or Tuesday, so that you don't have to worry about this one. All right. So far, so good.